to talk about, what regression is. Talk a little bit about classification too. Might not be in this slide, but probably in the Jupyter notebook, but a bit of. So two of the things that you're going to see recurring, they're going to be regression and classification, and I'm going to talk about them either in this video or the next. So for this slide, I'm going to focus on regression, the foundations of regression, and then we're going to talk a little bit about regression workflow, model interpretation and validity. That's where you're going to see things around errors, and how to measure errors. So that will kind of be what the focus of today's class is. And this is like week 4. So, and this is regression modeling and evaluation, predicting continuous outcomes and explaining model quality. So last week in week 3, one of the key focuses of that class was EDA, where we did our descriptive analytics, where we essentially grab data and then we mine it and then we present it, we analyze it. And the whole idea of EDA, is to understand what has happened in the past. So historical data, essentially. But today we want to move from descriptive analysis to supervised prediction. Now that we have data from the past, how can we kind of use it to begin to look into the future? Right? And that assumes that some of the environmental variables, right, are going to remain fairly the same or predictable. So if the conditions of the past do not change dramatically in the future, then I can use data from the past to predict what will happen in the future. That makes logical sense. The problem is if I have historical data and I try to predict into the future, but the future I'm trying to go into is a future that has changed in every bit, as it will, which is not very common, which is why where supervised prediction becomes very important. But then there's also that element where that's why when it comes to model predictions, when it comes to machine learning, deep learning, it's a very iterative process, because as we get into that future and we get new information, we keep gathering data and then we keep updating the model. And that's how your model continues to be relevant. But if you do not keep updating that model, then what happens is all of a sudden your model will be giving you errors because the conditions on the basis of which it was created have changed. So the second mission of this week is to build simple and multiple linear regression models, and then to evaluate prediction errors using meaningful matrices. So we'll see some of the metrics that are used in evaluating error, and what the whole idea of error is really about. And then we would interpret the coefficients, residuals, assumptions, and some limitations that you are going to run into. But again, what I'm going to do for this slide is kind of high level. When we get into the practice, which will be going down into the Jupyter notebook, you will see how some of the things that I discuss here are actually implemented in in practice. So some of the learning outcomes will be to frame a regression problem with features and targets. So if you're not really skilled in this art, something like features and targets will be completely alien to you. But we're going to talk about what's a feature, because it's from this whole idea of a feature that you have feature engineering, and then what's a target. And often when you do this analysis, right, and you're trying to build out models and all of that, one of the things you do is you typically split your data into two types of data. You have your training data and then your testing data, right? But I would mention there is also a third part of data, sometimes that is called your validation data. That's not included here because these are the two most important types of data. So when you get your data, if you're going by the two data category model, right? You might get your data and you would use 80% of your data, for example, or 90% of your data as your training data. And then the test data might be, you know, 20% or 10% of that data. You use this to train your model. And then after you've trained your model, you need to test that that model works. And then that's where you go bring your testing data, which the model did not see before, to test to see if the model you created actually makes sense, is accurate, and and performs to the standards originally set in your when you framed your problem, as it were. So then the other outcome will be to fit regression models with scikit-learn, which is one of those packages, Python packages that is used for AI, machine learning. So we'd use that, fit the regression model using scikit-learn, and then would evaluate with MAE, and we're going to talk about what MAE, MSE, RMSE, and Rs are. These are essentially parameters with which you evaluate your errors, right? So, and then we will use a residual analysis to diagnose model behavior. And then the final outcome will be to write a concise regression model report. Last week we did do a report for an EDA report. So the idea was to give you a framework for doing an EDA report. So for the regression, the foundations, the focus will be on supervised learning, regression framing, how to frame a regression problem, and baseline thinking that you need to solve these kinds of problems. So we'll start by understanding what exactly predictive modeling is. What is predictive modeling? Predictive modeling, is essentially the science and art of using historical data to estimate unknown or future outcomes. So we are just going to, like I mentioned, we pull data. Data is often historic because data is gathered based on events that have happened in the past. But then we want to use that data to figure out, what could happen in the future. We all don't have crystal balls, but then if we have um, some data, or we have some breadcrumbs from the past, we might be able to figure out what will happen in the future. So it's one of those things where you're asked to go find something in a vast space, but we drop crumbs here and there. So you have to investigate using those crumbs to try to find yourself to the castle. So that's what predictive modeling is and what it does. So, and then we have the idea of supervised learning. And we're going to talk some more about supervised learning. But in supervised learning, there is a need for input features and known target values, right? So you need to give me some things in that your data, some inputs, some variables to help me find the outcomes. So, for example, I want, if I have a model that has something like y is equals to 2x1 plus 3x2 plus 4x3, blah, 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 I need to know what those inputs are, my x1, x2, x3, x4. Because if I get all of those things, I can predict what my y is. So we need those input features. An example of that will be, say, for example, I am trying to predict what the price of a house should be in a particular area. Some of the input features I might need to make that prediction will be, I want to know how many rooms the house that you want is. I want to know when the house was built. I want to know some other important inputs, because with all of those inputs, I might be able to predict what the price of the house is. So in this example I've given right now, those input features are some of those critical information that you're going to give to me that can help me predict the target, my target value, which is my price. Now, there are all kinds of values I can pack in the features. Now, the idea of feature engineering is to decide which of those inputs actually move the needle, would affect price. So I could choose everything from the color of the house. I could choose things like the number of staircases in the house, the number of bathrooms in the house, and all of those, right? Some of those are all input features. Input feature engineering is to figure out which of those features are actually relevant, and then choose those features so that when I use those features and I play around with them, it will be very easy for me to find out the price of that house most easily. So the other thing here is prediction. It's not explanation by default. What you're trying to do in prediction is not explaining things. Prediction, you're trying to look into the future. You're not necessarily trying to explain. When it comes to explanation, that's probably better suited to EDA, which is your descriptive analytics, you know. So then the next thing, a model must be evaluated on data it did not train on, which brings me back to the previous slide that where we talked about we need to split our data into training. So this is the data. The training data is the data that the model sees, but the one it does not see is the training data. So you train with this, but then to really test whether that model works, you have to now use data that the model has not seen at all. Because sometimes you might train a model based on some training data, right? And then it's like it checks out very well, performs very well. The performance, the accuracy, everything works out well. But then when you go use it on a similar test data that it has not seen before, it fails spectacularly. So this, your test data can be a control of your training data to see that your model actually works well. A lot of people can sing at home and their mom would applaud them. Yeah, their mom is really very, knows them, is biased towards them as it were. So that's your training data. Mom's applause is essentially training data, right? To really test it out, you need to go meet Samuel Cowell, and go sing on the stage, and let's see whether you are as good as you claim you really are. In some cases, what the training data says ends up being what the testing data says. In that point, we really believe that you are good, that model is good. So I'll go to continue. So that's where I mean the model must be evaluated on data it did not train. Next thing, so a couple of things to know about regression. we talked about target. I think I kind of mentioned what target is, especially using the example about the house. You give me some information about the type of house you're looking for. Those would be my features, which are the inputs needed for that I need for prediction, you know. So if you give me all of that information, I can predict what the target is. And what my target essentially is continuous outcome to predict. What we are trying to predict is what the target is. An example could be we're trying to predict the house price, we're trying to predict your revenue, we're trying to predict your exam score. Now, if I to predict your exam score, some features I might need is how many hours do you study? Like how tenacious are you? How good are you at test taking? What's your IQ, if that's relevant? You know, all of those things. I need all of those inputs to build a model that can help me predict the exam score of everyone in that class. If I can gather data about everybody, some of these things I mentioned, and some of them might not be relevant, but the important thing is that they are all features. I gather all of that information, then I go into feature engineering to extract the things that are predictive of exam score, then that's how that happens. So features definitely very important, which is the input used for the prediction. Give me the inputs that you need to give me so that I can go ahead to figure out what the target is. So things like your size, the age, the location, or the number of study hours. If I know the study hours, which is a feature, I can predict your exam score. If I know the location, the age, and the size of the house you're looking for, I can predict the house price, especially if I have a lot of data around the area that you're interested in. So even something like the location, which is the area, is important. Yeah. So what exactly is the model? Model now is the function mapping features to target. So I need to create some kind of function. So if I say y is equals to mx plus c, that right there is a function, right? It's a function that maps the features to the target. So in y is equals to mx plus c, my target will be my y, mx plus c, somewhere in there, the x, right, is going to be my features, right? And then you have other variables that do other things, right, to keep the system working. You know, so that's y is equals to mx plus c is essentially my model, because it maps the features to the target. An example of a model could be linear regression there, and there are so many other models out there, right? So what is the error? So eventually with my um, model, I'm going to map out and I'm going to create something, all right? Once I create and I get that result I get is a predicted result. But in reality, I know what the answer is when I'm trying to build a model, so which is my actual. So to get my error, I want to say what is my actual minus what this model predicted. That is what will give me my error. And then there are different ways of capturing error. One of those ways of capturing error, you know, um, generally the mechanisms or the tools for capturing error are the things we refer to as error matrices, right? They kind of summarize the error, and there are different kinds of them. You have your RMSE, MAE, and all kinds of other error matrices. So this is an example of a simple linear regression model, right? This is just to capture an intuition. So in this example, Y is your target. Y is your target. And X is your parameter. but then we could have a model like this. Beta O is essentially the intercept. So if you draw a line XY and you draw a line across it, there is some kind of slope that is happening there, right? So that is what your intercept. But this is the intercept predicted when the predicted value when x is equals to 0. So at the point where x is equals to 0, right? This will be your intercept. Or rather, let me try. So if I had what I was talking about was slope. If I had an XY plane, in two planes, assume I have a straight line, which is my Y, and this is my X. The point at which the slope cuts through the Y line, right, is my intercept. So in this case, that's my BO. Because at that point where the line cuts through the Y, at that point, your X is equals to 0. So that would be your intercept. And then your slope will be, on that line, if I take my change in Y divided my change in X, that's where I get my slope. So it's expected to change in Y for 1 unit change in X. So it's have your line that goes through, and then you draw like a rectangle, right? And the change in Y divided by the change in X is what gives you your slope. And then your residual, the residual error not explained by the linear relationship. So when I create this linear relationship, I might get some kind of variance, the difference between what's predicted and what's real. That right there will be some kind of error that the relationship does not actively explain. So we throw in that value there to be like anything that this relationship cannot explain, that difference, we put it in as our error. So this is an example of a linear regression model. Then sometimes we have multilinear regression models, right? And that's where, for example, you have multiple features, right? It's one target, but you have multiple features. In this particular example, in the simple linear regression, here you had just one. You had just one feature, X. But here you have multiple features. So you have X1, X2, up to XP. These are all different things. This is the same thing as this. The only difference is that instead of having one feature, we are including something else plus a beta 2 plus beta 2 X X2 plus beta 3 X3 plus beta 3 4 X4 up to beta infinity, literally, plus whatever error. So each coefficient estimates the relationship between one feature and the target. So this explains the relationship between this feature and the target. This one explains the second relationship. So for the housing example I give, this might be number of rooms, right? This might be the age of the room, of the house, different values. But then the importance of each of those values, each of those features will be different. That's why you have these values here, right? So in other words, you're going to assign different values at this point. It wouldn't be the same because say the number of rooms might be more important than how many bathrooms, like how many bathrooms there are. The actual number of rooms might be more important. So if this is the number of rooms, and I intuitively or by experience, we know that it's going to have more weight. So I might include here 0.6, and then here I'll make it 0.2, right? And that's how that works. So each coefficient estimates the relationship between one feature and the target, holding other included features constant. This interpretation depends on assumptions and data quality. So typical workflow, again, we have our train and our test data. We split that data, some matrices, residuals, and then a plot. So this will be kind of what a typical regression model would look like. And you can actually copy this and test it out um, on your Jupyter notebook or something. But then we're also going to go do our own thing today, later. So this will be an example of simple regression. We're importing this package NumPy and we want it elsewhere in the code to now be referred to as NP. Then the next thing is we import pandas. Pandas is usually used to build your data frame. You get your data, but it helps it convert it into some kind of structured form. And then you have your sklearn. You're picking the model. So we're getting the regression model. Internally, it's referred to as linear_model, but we want to import it as this. And then we also have a model selector, which can help split the test data into training and test. And then this is also coming from sklearn, but then we're using a method called matrices, and then it helps us import mean absolute error, what we saw before, the MAE, and then this is your mean squared error, and then your R2 score. These are all measures that are used to evaluate the error. So those are the things that you need for this model. And then here you can have an input. This will be your input variable. In other words, I'm trying to get my features. In this particular place, we just chose one feature, which is the number of hours you're studying. And then this is your output, will be your final score, right? And then here you get your X train, you split your data into training data, which is this data, which is your study hours, you want to split it into two, X train and X test. This might be 80% of the data, 20% of the data. Then this is your Y train, which is your Y data that you're going to split into two, and then your test data. Then if you get all of that, then you train. To do that, you have to split the data X, Y, and then you randomly split it. In other words, you're going to, it's like shaking it up and splitting it. And then this is the model. What you're trying to do is I'm using this linear regression model that I imported here, and I want to fit this data, my X data, to my Y data, which is essentially like X, Y, and then you draw a line. How does X affect Y? And then to get your predicted Y, which is what you're trying to get, which will be equals to model.predict, and then you want to do that prediction. You are using that model, which is this model, and then you're calling up a method called predict, and then you're loading up the X test data, the 80% of the, this is after you've built your model. Now you're trying to test that data, and you're using this to test the data. Okay, this is for the regression, right? Then after you've done that, because this code continues, now you want to go do those various tests. You want to find your MAE, model absolute error. This is what you do, this and this. So there's already a code in the background, right, that can use this, provided you provide these two data pieces. MSE, which is your mean squared error. If you provide this result and your Y result, it will use both of them to come up with your MSE. RMSE, all it's doing is just it's squaring the MSE, because this is actually the square of this, right? And then your R2 score is, you give it the Y data, test data and Y predicted data, and then it will do its thing. And then this is essentially supposed to help you print out the results. And some of these tells you in what format you want to print it out. That's essentially what's going on here. So now looking at the regression matrices, right? In looking at the regression matrices, your MAE is the average absolute error. In plain language, what it means is that it's your typical means in original units. So the error is essentially the actual minus your what you call it, your predicted. So let's just look at this MAE, so that you see what the what do you call it, the premise. So this is what it's going to look eventually like. MAE, let's say you have 100 data sets, right? This N is supposed to be the number of data sets, right? 1 all over N, right? And then what you have here is your Y1 minus. So it's used to measure the difference between two continuous variables, such as a predicted value and an observed value. So if this is one value and the other is the other value, you subtract them, and then you take the absolute value of them, and then you divide by the number of data points, right? And then that's how you get your results. So all of this is hard coded into the system as a function or some kind of method, which is now used, here to get the results. So you see the two things we are looking at in this case is your Y tested and your Y predicted. So MSE, same thing. Let's look at MSE. MSE, mean squared error. Look at same thing here, Y minus yi minus yi hat. So y is the actual value, yi hat is the predicted value. So those two values, and then we square it. And when you square it, right, the interesting thing is when you square a large number, it becomes huge. So if the square of, say, 10 is 100, right? The square of 2, even though the difference between 2 and 10 is not a lot, but the square of 2 is going to give you 4. But the square of 10 is going to give you 100. So imagine square of 2 and the square of 100. Square of 2 is still going to give you 4. Square of 100 is going to give you something like 10,000, right? So what MSE is used when you want to amplify an error so that you can see the areas where the error is so large, right? That's what MSE is very good at. And that's why here it says it penalizes large errors strongly. So it helps you figure out where the large errors are. RMSE here, typical error with large error penalty. RMSE, let's go look at what RSME looks like, because it's just the squared, right? So this is what it is. So I get all of that information and I take the square root of it, right? That's what, and again, if you want to know some more about each of these matrices, just take some time and go do some reading on it. And then there is the variance, proportion of target variability captured by model. So if you look at the variables, right, like the difference between the various values, you can essentially figure a lot of that out with your variance. So again, these are different ways of interpreting the error that occur. So test, train and test split discipline. Training data teaches the model. So that's what you use to teach the model. You put it in there, you have your model, you feed your model with your training data. It will learn from that data, and then it will build out what you need. The test data is what you now use to test the outcome of that training, right? So essentially, because the test data does not see the model hasn't encountered anything like that. So it's another way of assuming. So now after I've trained my model and I want to run inference, right, in the real world, what is it going to look like when I'm going to run inference on data I wasn't originally trained in? That's the role the test data plays. So it says test data simulates unseen future cases. Evaluating or training data creates false optimism. So if instead of using test data, right, to evaluate my model, if I still go use test data, it might be telling me that everything is okay. In reality, when it's not okay, that's why you usually want to have your test data. So evaluating on training data, doing my evaluation of my model using training data creates false optimism. So do not do that. So for time series is essentially data that was collected over time. In other words, so let's say I'm looking at velocity, right? And I'm trying to figure out the velocity of something over time. So now I'm going to have only two variables, right? The velocity and time. So that kind of data where the two main variables are, the major variable and then the dependent variable, where time is a dependent variable. For those kind of things, we refer to them as time series. So for time series, never rapidly split across time without care. In other words, usually in analyzing time series data, right, you have to split the data into chunks of time. So let's say I'm collecting data at 1 data point per second, right? And I do that. In other words, in 1 minute, I would have collected 60 data points. Collected data at 60 points, right? Now, when I'm going to slice that data to analyze it, usually because in time series, you have to split the data. He said never randomly split data across time without care. So you need to be careful how you're chunking up that data, especially if you're going to use it in a case like this, because if you don't chunk it right, it might not be representative of the train, and then it will be giving you some error that does not make sense. Residual analysis. So residual is actual value minus the predicted value. So that's your actual value minus the predicted value is what we refer to as residual. So good residual patterns should look roughly random around 0, right? Curved patterns suggest non-linearity. And this is what happens when you get a residual value and you try to plot it. It should be random around 0. But if you get a curved pattern, then you run into non-linearity. So let's look at non-linearity. Non-linearity. Notice? So look at it. In data science and statistics, non-linearity occurs when the relationship between the variables cannot be represented by a straight line, right? A residual is the difference between the observed value y and the predicted value y prime. When predicting complex curve data using a basic linear model, right, the residual will display non-random symmetric patterns. So that's what you're seeing here. So when analyzing models, the most common diagnostic tool is a scatter plot with residuals on the y-axis and fitted values on the x-axis. So the ideal scenario when you're trying to represent an XY plot, right, using XY graph using scatter plot, the ideal scenario is if the model is properly fitted, residual should show a random equal scatter evenly plotted above and below the horizontal line. In other words, if I plot something XY and I draw a line that tries to follow my scatter plot, right? I should have random dots around it. That's what's supposed to happen, ideally. But if the plot on the residual, if the points on the residual plot, that plot that I made, they all of a sudden begin to curve upward, downward, or take on an inverted U shape, often called a bow curve or a smile. It indicates that the underlying relationship is nonlinear. So you're plotting something and you want to, it's supposed to go through some kind of straight line, right? And all of a sudden, instead of doing that, it's you are literally having things like this happen, right? Then in that case, what you have, and you can see it here too, then all of a sudden you have a case of non-linearity, staring you in the face. That's what that point was. So, so curved patterns, as you see, suggest nonlinearity. Increasing spread suggests heterosyndacity. Then let's go look at heterosyndacity a little bit too. Increasing spread. The spread is like all of a sudden going huge. So look at this. So it says heterosyndacity residuals occur when the variance of an error term in a regression model is unequal across different measured values, often forming a funnel or cone shape on a residual plot. So why exactly is it happening? Because this is what it will look like. So what you're expecting is supposed to be something like this, but this is what you're getting. And that's why it's referred to as heteroschidastacy. This is what you're supposed to get, which is your homoschidastacy. So that when you plot a line through this, some of the points will be around and around, but they are hugging closely to that line. But here is literally it's beginning to create like a funnel. Yeah, you can see it here too. It's creating like a funnel. This is what you would expect, but this is what you're getting. Look at something that actually exaggerates it, right? So, and this is why it happens. Data scale effect. Data sets spanning a wide range of values naturally tend to exhibit wider spread at higher values. Higher incomes have a much wider spread of discretionary spending than lower incomes. So exactly when certain values, right, if you have a wide range, all of a sudden, there are certain data sets, right? And it gives us a specific example here with higher incomes. People that have higher incomes have more flexibility, right? At the lower income rung, people are kind of struggling. They don't have discretionary income. So when you're trying to plot a graph of, say, how they use their money, it will be tighter at the lower end. But then as you go up there is a spread, So there are other reasons why it happens. And if you're interested in this, see exactly what I did and you can just go read up on it. Large residuals, right? If we have a residual that is large, it may indicate outliers or missing features. So I have outliers. Let's actually look at an example of an outlier. So this is an example of a huge outlier. It's out there. Everything seems to be calculating around here. This is a huge outlier there. So you said large residuals may indicate outliers or missing features. So if we want to do a residual plot, this gives you an example of how to do a residual plot. Your residual will be your y-test, and your y-predicted. This is the test data, and then this is your predicted data, and then what else? Your predicted, your original outcome, what we know is the correct answer, and this is your predicted outcome, right? So all we need to do is to plot that. Dot scatter means we are using a scatter plot to do it. You put in your y, your predicted, and then your residual. Remember, your residual is your test minus this. So you plot this against this, and then that's how you get. So your x on your x side, right, which is horizontal, is going to have your predicted value, and then your y side is going to be your residual. And then this is the title, which is your residual plot, and you get your answer there. So I think this is most of what we will cover right now. Continue later, but let me just touch on a few more of these before we go, because this is writing your defensible regression model reports. But let's touch on this before we continue or go to the next steps. Linearity. I showed us non-linearity. What non-linearity is? Linearity just means that the relationship between two or more variables is kind of linear, right? It's a straight line. But if it's non-linear, then you see it's curving, and there are different kinds of non-linearity. So here it suggests that relationship is approximately linear. What can go wrong? You can actually have a systemic residual patterns where there's a systemic error and everything is following the same straight line, and you think you're correct, but you're actually not correct. There's an error. The only thing is that error is systematic, and then it's throwing off systematic residual patterns. That's what can happen with non-linearity. So there's something called independence. The errors can be, for example, independent, and then you can have time or group in independence, right? And homoscedasticity, I think we talked about that, where we talked about heteroscedasticity. But in homoscedasticity, I showed us where you see that the data is clogging together. Let's look at it again. This is an example of homoscedasticity, right? This is homoscedasticity. The data they are mapping around. But let's do heteroscedasticity. Right? So in heteroscedasticity, all of a sudden, this is heteroscedasticity. It's literally winnowing, and look at other examples here. This is homo and this is hetero when you're looking at those errors. Normal residuals, error roughly normal for inference. If you have normal residuals, the error is, roughly normal. No severe multicolority. The idea of multicolority is also a very important one. So let's just look at multicolority, because it's something that shows up. Multicolority. So in regression analysis, residuals are the difference between observed and predictive values, which we already talked about. Multicollarity occurs when the independent variables are highly correlated with each other. No, we're not talking about the independent versus the dependent. This is the independent variables themselves. They have a strong correlation. At that point, right, things don't make sense anymore. So when you have two things, right, that are supposed to, there needs to be some difference between them, but both of them are kind of matching. You have a case of multicollarity, and you want to, in some cases, drop one of those. So so coefficient interpretation. So we talked about the coefficient, and I showed you how different variables can have different weightings, right? A coefficient is not automatically causal. Just because you have the coefficient have a particular value doesn't mean that that value is tightly aligned to the value of the variable, right? So the point is that you interpret coefficients only in context and with assumptions stated. Scaling and encoding affect coefficient meaning, and these are some of the things we need to talk about when we do like the practice, but just hold that thought. Multiple regression coefficients are conditional on other features included. So especially, let me see, where we're talking about yeah. So you can see just B alone does not automatically define what X1 will be. The overall impact of B on X1 is also determined by B1, B2, B3, B4, B with, so all of these things work together, right? So that's why it's like you have to be careful how you interpret the effect of one coefficient on a particular parameter or feature. So where did we stop? So that's why it says multiple regression coefficients are conditional on other features included. So in writing your report, right, for what do you call it now? In writing your report, the report that we just mentioned, right, you have to be able to state what the problem is. And we're talking about your regression report. What continuous outcome is what am I trying to predict? So giving an example, we're talking about house prices. I want to build a model where if someone comes and gives me all this input, I can immediately predict, gives me the location of because comes value, gives me the size of the house, the age of the house, and all of those things. Once I go into my system, I can actually predict it. And the difference between what I predict and what the actual value will turn out to be will be statistically insignificant, right? So if I want to write a report like that, the first thing is I want to identify what the problem is. And the first thing is like, what continuous outcome is it that I'm trying to predict? Now, the next thing I want to do is I want to state my data sources, the source of the data, the targets, the features, and the sample size. All of that should be captured there. Then I'm going to say the method, right? I'm going to decide what model I'm going to choose, what split, how I'm going to split my data, and how I'm going to pre-process that data. Sometimes you might actually get several models, run the models, and figure out which of the models is best. But in your report, you'll be like, oh, I dabbled with this model, and that model. But after carefully looking out done my diagnostics, right, I choose this particular model. So some of the matrices, you need to get the values, get the matrices and then interpret them. Then you go into your diagnostics, where you have to look at your residuals, your assumptions, and the errors. And then you have to do your conclusion, the usefulness, limitations, and your next steps. So this will be practice writing a defensible regression model report. So these are some of the things that you would have to do to get to that point. So I think we are going to stop here and take a little break, and hopefully come back and finish the other side. I shall talk to you soon. Let's say in the next few minutes.
Okay.